In this chapter, we will cover permeability and seepage, discussing flow of water through soils. As the name implies, permeability means ability to permeate. Permeate is passing through. Here, we are talking about water passing through soils. The ideas also apply to any fluid passing through a porous medium. When the soil grains are densely packed, it is difficult for water to flow through the pore channels, making the permeability low. Here, water is flowing through an embankment from upstream reservoir to downstream. Let's see what Bernoulli's equation says about the energy of a water molecule on the flow path. The water molecule has mass m, velocity v and is under the pressure P. Its energy consists of three components: kinetic energy, strain energy, and potential energy. Kinetic energy comes from the velocity, strain energy from the pressure, and the potential energy from the elevation with respect to a datum we select. Dividing by mg and expressing the energy per unit weight and unit of length, Bernoulli's equation boils down to total head equals velocity head plus pressure head plus elevation head. From this numerical example, we see that velocity of flow is small and hence the velocity head becomes negligible compared to the elevation or pressure head. Therefore, for flow through soils, we can neglect the velocity head and say total head equals pressure head plus elevation head. Let's consider 2 points A and B on the flow path. If the flow is from A to B, the total head at A is higher than the total head at B. Energy is dissipated in overcoming the frictional resistance provided by the soil along the flow path and hence is the total head loss from A to B. At any point within the flow region, pressure head equals pore water pressure divided by the unit weight of water. Elevation head is the height above the selected datum. Either of the two can be negative. The hydraulic gradient between A and B is the total head loss per unit length along the flow path. Thus, It is the total head loss from A to B divided by the flow path length AB. It is denoted by I. If I is 0.3, that means 0.3 meters of total head is lost along the flow path for every meter. You can see that the head loss occurs only within the soil. There is no head loss within the water columns. The entire head loss HL occurs across the soil sample of length L, and hence the average hydraulic gradient across the sample is HL on L. From this exercise, you see that no matter where you select the datum, the hydraulic gradient is the same. Without any calculations, you should realize that the total head losses across the soil samples A and B are 300 mm and 175 mm, respectively. This is after Darcy, a French engineer from 1856. He noted that when there is laminar flow through soils, the flow velocity is proportional to the hydraulic gradient. From now on, we will call this flow velocity as discharge velocity. Since hydraulic gradient has no units, the proportionality constant K has the unit of velocity. K is called the hydraulic conductivity or permeability of the soil. It is commonly expressed in centimeters per second or meters per second. In 1901, Forsheimer suggested that hydraulic gradient I versus discharge velocity V relationship can be better given by I is equal to a V plus BV squared. Here, A and B are constants. Forsheimer's relationship covers the non-laminar region as well. You will remember Reynolds number you came across in fluid mechanics for pipe flow. This is a dimensionless number. We use the same expression in groundwater seepage and replace the pipe diameter by D50. We can say if the Reynolds number is less than 1 in flow through soils, it can be assumed as laminar flow. In this numerical example, you can see that in the coarse gravel, Reynolds number is 600, which is much larger than the limiting value of 1 and hence the flow is not laminar. In the silt, Reynolds number is 0.4, which is less than 1, and the flow is laminar. Here are some approximate cutoff values for permeability in centimeters per second between different soil groups. They differ by orders of magnitude. For coarse-grained soil, K is a function of the void ratio E or the effective grain size D10. From the top row, you can see that the flow is no more laminar in gravels. Silts, sands, and gravels are well drained, and clays are poorly drained. When the hydraulic conductivity is less than 10 to the power minus 7 centimeters per second, the soil is practically impermeable. In 1930, Hazen suggested that for clean uniform sands, K equals C times D10 squared, where C equals 1, D10 is in millimeter, and K is in centimeters per second. This is very approximate. In clays, log K is proportional to log of the void ratio E. When there is a surcharge on top, void ratio decreases and understandably the hydraulic conductivity decreases too. However, the extent of the reduction in K with surcharge depends on the soil type. The reduction is more pronounced in clays than in granular soils. We will show you that when water flows upward, the effective stresses are reduced and the pore water pressures are increased. Similarly, when the water flows downward, effective stresses increase and pore water pressures decrease. Let's consider 3 scenarios where we look at the same point X and identical soil specimens of length L. The first one is a static case, where there is no water flow. In the second and the third, there is downward and upward flow, respectively. during upward flow in a granular soil, when the hydraulic gradient increases to the critical hydraulic gradient, the effective stress becomes zero and the soil's grains are barely in contact and the granular soil fails. This is known as quick condition. The critical hydraulic gradient IC is the ratio of submerged unit weight to the unit weight of water and is generally around 1. Permeability tests are carried out in the laboratory on cylindrical soil specimens that are reconstituted or undisturbed. For coarse-grained soils, we do a constant head permeability test, and for fine-grained soils, we do a falling head permeability test. In a constant head permeability test, the total head loss across the soil specimen is maintained constant throughout the test. In falling head permeability test, the total head loss across the soil specimen decreases with time. In a constant head test, Q volume of water is collected over time T, flowing through the soil specimen of length L and cross-sectional area A. The head loss across the specimen is H. From Darcy's law, it can be shown that K equals QL on HAT. In falling head test, the head falls from H1 to H2 over a time T. Small a is the cross-sectional area of the standpipe, and capital A is the cross-sectional area of the specimen. In the field, in situ permeability can be determined from a pump-out test. Here, water is pumped out from a well and the lowered water levels are observed from two observation wells at distances of R1 and R2. At steady state, H1 and H2 are recorded and the permeability determined. Now that we have finished discussing permeability, let's get on with the next part, seepage. First, some key terms we will be using. Streamline is the path of a water molecule. Equipotential line is the contour or locus of the points with the same total head. There are thousands of streamlines and equipotential lines in the flow region. Flow channel is the passage of water between two adjacent streamlines. These are the governing partial differential equations for seepage in 2D and 3D. In 2D, if the soil is isotropic, the permeability is the same in all directions and hence Kx equals Ky, and we have Laplace's equation, which implies that the streamlines and equipotential lines are perpendicular. Here, we show that the flow rate is given by Q equals KHL times NF on ND, where NF equals number of flow channels, ND equals number of equipotential drops, and HL is the head loss from upstream to downstream. We also see that the flow net consists of curvilinear squares formed by the streamlines and equipotential lines intersecting at 90 degrees. Here is the flow net for flow around a sheet pile, generated using a software. Ideally, you should be able to fit in a circle within a curvilinear square, touching all four sides. The circles will be of different sizes. In this example, NF equals 4 and ND equals 8. NF or ND need not always be integers. Here, we have 3.8 flow channels, as the bottom channel is not a full channel. I have the habit of taking the tailwater or downstream water level as the datum. You may have noticed this in the previous slides. Both flow nets shown here are symmetrical. Therefore, we can analyze half the geometry, which gives half the flow rate. In hydraulic structures such as dams or sheet piles, the exit hydraulic gradient is the maximum near the structure. When they are in granular soils, when the flow is upward and the exit hydraulic gradient exceeds the critical hydraulic gradient, the soil loses its strength and fails at that location. First, this failure happens at the exit, right next to the structure, and quickly progresses upstream, and forms a pipe of water that can flood the downstream. This can be catastrophic, and there have been many failures reported worldwide. Always make sure the exit hydraulic gradient is very much less than the critical hydraulic gradient. Protective filters made of granular soils are used in earth dams, retaining walls, trenches and drains. They serve two purposes which have contradicting requirements: retention and permeability. The pore channels have to be small enough to prevent the fines from the soil being washed through. On the other hand, the pore channels have to be large enough to allow free drainage and prevent any buildup of pore water pressure. We have to strike a balance between the two. Retention criterion requires that D15 of the filter is less than about 4 to 5 times the D85 of the soil it protects. Permeability criterion requires that D15 of the filter is greater than 4 to 5 times D15 of the soil.